Good evening, class. Today we're going to continue our work with physics with one more example, and this time we're going to start working with collision restitution, and specifically how do we do elastic collision. So when two objects smack into one another, how do we make them fly apart in a realistic manner? So how do we manage to emulate that using the actual physics? So we have another example game. It should be fairly familiar by now. We have a list of balls, which are these ball sprite objects. We are setting our game width and game height. This is a little different. We haven't done it this way before, but we have just a static class that has some read-only constants defined, and that gives us the ability to kind of set it here and also use it in some of our calculations inside this ball sprite. So let's real quick kind of walk through what we're doing here. We set up our game width and height. Initialize our balls. The balls have a center, a velocity, and a mass, and we're just giving random values that fall into a reasonable range for those. We're going to load all the balls, and we're going to move all the balls. And then we're also doing some collision detection here, and we're using a very similar method to the circle-on-circle collisions. That's actually exactly what we're using, but it's put into the ball sprite instead of its own class. And notice that we're nesting two loops as we're doing this, and this shouldn't be that unusual, but you may have not seen it done this way before. So the outer loop, we're going from 0 all the way to the last index. The inner loop, we're actually starting at index I, so whatever I we're on here, plus 1. And this is basically allowing us to check the very first ball against every ball after that ball. Then we're checking the second ball against every ball after that ball, the third ball after every ball after that ball. And the benefit to this approach is that we don't end up checking each ball against the other ball twice. We're only checking them once. Whereas if we said I from 0 to balls.count and J from 0 to balls.count, we'd actually check twice. We'd check ball 0 against the last ball, and when we got to the last ball we check it against ball 0, so that you actually would do quite a bit more work. This saves us some work there. And if the balls are colliding, we set this colliding property on the ball to true, just so we can have a visual indicator, which we'll see here in a moment. And then we have our sprite batch begin and end with the draw calls in between. Now the ball sprite looks fairly familiar. We have a texture. We are defining a few extra values, a vector 2 to use for the origin, a floating point number for the radius and for the scale. This colliding boolean we saw set, so it's just a property. The center is a vector 2 property, and the velocity is a vector 2 property. And then the mass is also a property, which we're using the radius as a private backing variable for that. And then when we set that radius, we're also setting the scale, and we're just taking, since our sprite is 64 pixels wide and 64 pixels tall, our radius is just half. Our scale is going to be the radius of the ball divided by the actual radius of the sprite. So that tells us how much we have to scale up the sprite to match the radius that has been specified. And then our origin is just going to be to the center of that sprite, which again is 64 by 64, so half the way through would be 32 by 32. And then loading the textures, nothing new there. Moving is pretty straightforward. We take the position plus equals velocity times the elapsed time. So again, something we've done before. This bouncing balls off the edge of the screen, we did this in the very first game that we worked on. So we're just basically checking to see if we've reached the edge of the screen minus the radius, or the radius buffer, so that when the very edge of the ball touches the screen, we just reverse the velocity in either the X or the Y direction to get it to bounce off. And then at the very bottom of this update, we just always set this colliding flag to false, which, remember, it gets set to true after we've updated the balls. So we update the balls here, which clears that flag, and then if we happen to be colliding here, and then we set it back to true. And that means it's true when we get down into drawing, which is important, because we're actually defining the color we're using for the ball based on that colliding boolean. So if we are colliding, we're going to apply a green color on top of this largely red ball, which is going to make it much closer to black, a really dark gray. Otherwise, we'll just use color white. So we just use the Trinity operator here to decide which one to use, and then we draw. And notice we're using one of the more expanded versions of this, where we provide the position, a source rectangle which we set to null, so we use the whole texture, the color that we defined up here, and then a rotation value, which we're never rotating this, the origin vector, and then the scaling value, which we calculated up above, and no sprite effects, and setting the depth layer to 0. And then here's the collides width, which, remember, the mass and the radius are effectively the same for our balls, so we just add the two masses, see if that's bigger than the distance between this ball and the other ball's centers. And if that's these radii added together are bigger than that distance, then we know that these two balls are colliding. Alright, so let's go ahead and take a look at what that looks like in practice. So here we have 5 balls moving around the screen, and notice as they collide they flash this darker, almost black color. Then as soon as they stop colliding, they're back to being their regular reddish orange cells. So, coming back to our physics game, we want to handle the collisions. And whenever we have those two balls colliding, we want to decide how they need to bounce off each other. And if you read the textbook, you would have seen the formulas that we use to actually do that, which take into account the mass and the initial velocities, and we're utilizing the fact that energy is conserved and that momentum is conserved to basically provide two equations for our two unknowns, the velocity of the two balls after the collision. And then we can use those equations, we can calculate exactly where how much of collision that should happen. Now what's interesting is that those equations are really for one dimension, and we have two potential dimensions here because our balls are moving around the XY plane. But we can treat them as one-dimensional collisions if we align the coordinate system with the collision axis, so the axis between the two objects that are colliding. And that's actually pretty easy to find. We can actually get that. So let's define a vector 2. And we will just take the first ball and then subtract from it the second ball's center. So this gives us a vector from the center of the first ball to the center of the second ball. And now to find how much of an angle there is between wherever that collision line is and the actual centers of the balls, we're going to find the angle between those two. So that is going to be, or we can calculate that using the relationship of cosine of that angle to the dot product of the two vectors. So we can do the dot product of the two vectors over the sum of the magnitude, or the product of the magnitude of the two vectors equals cosine theta. So we could take cosine theta and pull off the cosine, make it theta equals the inverse cosine, or arc cosine, of the dot product of the two vectors over their magnitude product. Now the magnitude product, if they have a magnitude of 1, is just going to be 1 times 1, or 1, so it will cancel out if these are unit vectors. And it's actually really easy in MonoGame to make a vector into a unit vector. We just invoke its normalize function, and that will normalize, basically divide the length of both the vector, the x and y components, by the sum of their magnitude, which makes it unit length, or length 1. So then we can say float angle is going to be math dot, and this is actually in system dot math dot a cosine. And then inside of this we just need the dot products because we got rid of the magnitude, because these are both now a unit vector, or the collision axis is a unit vector, and we'll use a unit vector in the x direction as well. So vector 2 dot dot is the method for computing the dot product of two vectors. We'll use that normalized collision axis, and then we'll use vector 2 dot unit x, which is a unit vector in the x-axis. And then, of course, because this is system.math, it actually calculates as a double, so we have to cast it to be a float. to allow our angle to actually throw away some of the precision that it would normally calculate with. And that gives us the angle between where the collision axis is and the x-axis is. And what we're going to do is we're just going to rotate our collision axis so that it is aligned with the actual x-axis. And we can do that using another vector2 method, which is vector2.transform, which transforms a vector using a matrix. We're going to transform the velocities are actually what we're after. So balls I dot velocity. And the matrix we're going to use a create matrix dot create rotation matrix in the z direction. That's out of the screen. And then we'll put our angle in here. Then we'll do the same thing for the other vector, the velocity of ball j, and these values are the initial velocities. So I'm going to call this u1, u0, and u1 for our two objects. So we have rotated, by rotating that, we've basically changed the coordinate system. So we can think about our coordinate system now where the x-axis is actually aligned with the collision axis, which means that all the transfer of momentum is going to happen along that x-axis. So our velocity after the collision, or v0, and the velocity of the first item after the collision are going to be in the x component based on those equations that we saw. So let's go ahead and type those up. So v0 dot x is going to equal the mass 0 minus mass 1 divided by mass 0 plus mass 1. We take that whole value times u0 in the x direction, and then 2 times mass 1 divided by mass 0 plus mass 1 times u1 in the x direction. And these masses, by the way, we're going to pull those out. Float m0 is just going to be balls I on mass, and float m1 is going to be balls j dot mass. And we could actually type balls I and j dot mass for these, but it's handy to just use a very shorthand notation because you can see these equations are not small. And then v1 dot x is going to be m, or 2 times m naught divided by m naught plus m1 times u naught in the x direction plus m1 minus m naught divided by m naught plus m1 times u1 in the x direction. So you can see these two equations are pretty much mirrors of each other, which is what we'd expect. It's actually setting us up with the idea that this is proportionate. The amount of energy that one's going to end up with is proportionate to the amount of energy the other one's going to end up with. So we're distributing them based on a proportion based on the mass. Now, if they happen to be the same mass, this actually becomes much easier because this becomes 0 divided by the sum of the masses. So this whole term drops out, as does this term, and you're left with 2 times the mass of 1 divided by the mass of 1 plus the mass of the other, which is also 2 times the mass of 1. So they're basically, these numbers cancel out or divide into 1, and you just end up with the velocity, the old velocity in the x direction and the old velocity in. So basically they end up swapping their velocities if they're the same masses, which would be like if you're working with pool table balls, that would be that case. So, but if your objects have different masses, then you have to have this proportional relationship set up. Now, the velocity and the y-axis, because this is not in line with the axis of collision, actually doesn't change at all. So velocity not in the y direction is the same as the initial velocity in that direction. And the same for velocity 1 in the y direction is u1 in the y direction. So that's the reason we want to rotate this, is it makes this much easier. You can still do it without rotating, but then you've got to do a lot of trigonometry. And we kind of sidestep that by treating this, moving this coordinate system. Now, that does mean that we have to move the coordinate system back. And so we'd say balls of I is going to be vector2 dot transform. So we're going to take our new computed velocity naught, and we will transform that back by creating a rotation in the z direction. And this is going to be the inverse of the angle we used to get here, so negative angle. And oh, not the ball, but the ball's velocity. So this is the updated velocity. And the exact same transformation for the second one. So we're basically just twisting the whole world to do our calculation, then twisting it back. This also means that even though we're only changing the velocity in one axis, when we twist it back, it's actually changed both the x and the y a little bit. So it actually really does reflect what we would expect. And once we've done that, that's really it for this handling of these realistic collisions. So let's go ahead and run this game again. And notice when these two bounce, they just bounce right off another. Now, there is one little challenge there, and you saw that if they interpenetrate a little too much, then they can actually get stuck on one another. And that's a problem you'll occasionally see, especially when one's moving rather faster than another, like that one just actually got stuck and kind of orbited around the first one for a little bit. So depending on the type of game you're building, like if it was an asteroids game, this might be perfectly fine behavior. However, if you're doing something like a pool game, obviously that's not very realistic. So there would be an extra step you would do after this, where you would basically figure out how much, either push them apart enough that along these velocity vectors that they would no longer be touching before we moved on from here, or we could actually calculate what moment those balls actually smack together up here and reverse that, or we could cheat a little bit and just kind of back them out a little bit now. So for example, we know that what our elapsed game time is, and we know what our old velocities were. So we could say, for example, balls I dot center minus equals balls velocity times game time total seconds. And we can do the same thing for the J. And of course, these have to be cast to be floats. So what this does is, what we're doing is we're basically reversing the velocity, the original velocity, which we've actually already overset at this point. So we'll move this up a bit. We'll do this before we actually even make changes. So all that does is that undoes the motion that they made in this frame. So now they haven't hit each other yet, and they're still apart out, and we've changed their velocity. And depending on how fast they're moving, this can look just fine, or we'll have a noticeable stop when they're not quite touching and then separate. Oh, and even then we still had a little bit of too much. You know what? I think we might have our rotations backwards. I think we need to rotate negative here, positive here. Let's see if that makes a difference. Yeah, that's much better. So let one of these very massy ones hit one of these lighter ones. See what happens. Still got sucked in. So like I said, this is actually a cheat. A better way of doing this would actually calculate when that collision actually occurs and only apply enough time to undo that collision and then reapply that extra time with the new direction. And if you do that, your balls will be much more realistically behaved and you shouldn't have that problem. But that's basically in a nutshell how we can set up this kind of elastic collision. Now in the real world also, no collision is actually going to be perfectly elastic. There will actually be a certain amount of energy that's lost as heat and sound when we have a collision. So one of the things you can do is you can take a little bit off both those velocities, just the same amount to emulate that loss. That's an easy way of doing it. If we have more than one body that's colliding at a time, there's actually no good or easy way to deal with that in a video game. So what we usually end up doing is we solve for just pairs. So if there's three, we solve for A and B, we solve for B and A and B, B and C, and then A and C. And then after we've solved for those, we check to see if they're colliding. If any of them are still colliding, we solve again. And we just keep kind of pushing them apart until we've managed to get them loose. Now that's not very accurate, but it often will look good enough to get us by in a game situation. If we want to do realistic physics beyond this level, we're really getting to the point where we're starting to talk about using potentially a physics engine, which normally we would pull in an outside library that was built specifically for solving physical constraint problems like rigid body dynamics, as well as other things like simulating ropes and chains and those kinds of actions. And when we use one of those physics engines, basically what we're going to do is we're going to define a rigid body that usually has a mass and a center and kind of a bounding volume. So all the pieces we've already seen, and then it will take care of updating on those based on the acceleration, the velocity, and other properties that are applied to them, handle the collisions for you, and tell you where those rigid bodies should be in every frame, and then you just draw your actual sprite where that rigid body tells you they should be. And there are a handful of physics engines that were actually built in C# specifically for use with XNA. The Farseer engine and the Aether physics engine both were directly built for XNA and use natively the same vector and matrix types that XNA uses. So those would be good choices if you want to go that way. And that really wraps up our talk on realistic physics. So next time we'll talk about maybe some not realistic physics, the kinds of physics that we see in things like platformer games. And well, we'll see you then.